Okay, here we go. Hopefully this works. So answer the following questions about magnesium hydroxide. At 25 degrees Celsius, the value of the solubility product constant, KSP, capital K, for magnesium hydroxide is 1.8 times 10 to the minus 1. Calculate the number of grams of magnesium hydroxide that is dissolved in 100 milliliters of a saturated solution of magnesium hydroxide at 25 degrees Celsius. So, again, you see capital K, you're going to write out the equilibrium formula or expression. So, we'll start out with the chemical reaction. MgOH2, solid. When it dissolves in water, what's the ions present?
Mg2 plus.
Mg2 plus, and how many hydroxides?
Two.
Yep, 2 hydroxides. Okay, so that's the dissolution process. And if we write out write out the K expression, we call it SP because this is a solubility product. This is dissolving into water, and it would be Mg2 plus and OH minus to the second power over the concentration. Oops, and I almost fooled myself, over nothing or over 1 because this is a solid, so we don't include the solid. So there's our KSP, right? And they tell us that this is a very small number, 1.8 times 10 to the minus 11. Right? And they want to know how many grams of magnesium hydroxide dissolve into water, and all they tell you is that KSP. So you need to set up an ice chart. So I'll set that up right below. ICE. Again, solids we ignore. So we start out with 0 of it dissolved in water. And how much dissolves? You guys remember we just set this up like in X. Yep. So some of it dissolves. We don't know how much. So then how much hydroxide will you get?
Also X?
Careful.
Or wait, no, 2X.
Yep, because you get 2 hydroxides for every magnesium. So it's always going to be double the amount. So we just say 2X. So then you end up with X and 2X. Okay, so we know the final concentration at equilibrium are those 2 values, so I plug them into my expression above, right? So I plug them in here and here. So I have X times, parentheses, 2X squared equals 1.8 times 10 to the minus 11. Okay, so those are my equilibrium values, and then you don't get tripped up here. What does this side simplify to?
2x cubed.
Careful, because this is 2x times 2x.
4x
Yeah, there you go. You get 4x cubed, right?
Yeah.
So you get 4x cubed equals 1.8 times 10 to the minus 11. And then you can solve for x. Yep, divide by 4. Take the cube root. And again, this is a stretch because this is actually unit 8. So they said that this wouldn't be on the test. However, being able to write ice chart, that's in unit 7. So this is kind of the bleed over. You probably won't have to take the cube root. I can't guarantee it, but I'm 99% sure because this unit falls in, or this content falls in unit 8, they will not make you solve a KSP equation. But setting up an ice chart would be considered okay. So they ended up getting x equals 1.65 times 10 to the minus 4th. Okay, and so quick reminder, when we're setting these up, and these are square brackets, and you're doing your ice chart, all these x values and all the things listed in your ice chart are in molar. Okay, so the question is, how much in grams of MgOH2 dissolves in 100 milliliters? So we know that at equilibrium, that's the final concentration, right? That's the concentration of magnesium. So you need to now back out moles and then mass, right? So how do I convert molar? How do I convert molar into moles?
Isn't it
you multiply it.
Multiply it by what?
The liter.
Yep. So then Savannah was about to say it. How many liters am I going to multiply it by?
0.1.
Yep, 0.1. So I end up, it basically moves my decimal place one more time. So I end up with 1.65 times 10 to the minus 5 moles. And then they give us the molar mass. It said the molar mass was 58.32 grams per mole. So I multiply the amount of moles. Oh, and I kind of glossed over this. I used the 1.65 because it represents, let me scroll back up if I can. It represents how much magnesium ions are dissolved and what's the ratio of magnesium to magnesium hydroxide. That's
1-to-1.
That's the 1-to-1. So like I know we did also technically you could have doubled it and solved for this, but because it asked about magnesium hydroxide specifically, then I need to pick the value for concentration that matches or has the same ratio as magnesium hydroxide. So that's why I used 1.65. So 1.65 times 58.32 grams per mole comes out to, and they round it now. They actually wrote it with 2 sig figs, 9.6 times 10 to the minus 4th grams of MgOH2. And they did that because I think their KSP value that they gave us only had, it only had 2 significant digits. So they rounded down to 2 significant digits. Okay, so again, a lot of math, but I think it's more setting up the ice table that's the important part. Okay, B, we'll zoom back in. Says the energy required to separate the ions in magnesium hydroxide crystal lattice into individual ions, as represented in the table below, is known as the lattice energy. So, as shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. So magnesium and strontium both dissolve, and one of them say takes more energy to dissolve, this guy, magnesium, and this one is held together with less energy, so it's easier to dissolve. So why are some reasons strontium hydroxide would be easier to dissolve? And probably good. Where are strontium and magnesium on the periodic table?
Let me pull up the periodic table.
Yep. You guys look, and I'll wait. I can scroll down.
I'm assuming magnesium is there. Where's strontium at?
What is strontium? Is it SR?
SR, yep.
It's number 38.
Okay, number 38, which is right here, SR and Mg. And remember, this MgOH2 was strong. Okay, meaning it had a high lattice energy. And then strontium hydroxide was weak because it had a smaller lattice energy. So why would strontium hydroxide be weaker than magnesium hydroxide?
Is it because it's lower?
Yeah, it has something to do with lower. So it's lower on the periodic table. So what's your next, like, if you had to jump, why is being lower on the periodic table? What's that do to the ions?
Is it because there's more electron shells?
Yep. So what's true? That affects what about what physical property does having less or more electron shells? What does it change about that ion?
It makes it larger.
Yep, is larger because it has more electrons because more shells.
So it's further away from the OH, so the bonding isn't quite as strong.
Correct. There you go. So it has a larger bond distance, or you can say it's further from the OH ions. And in terms of ions, when you have a plus and a minus, okay, here's the weird thing, right? We talked about all the stuff last time about how polar things dissolve polar things and like dissolves like, but when you're talking charges, when you're talking magnetism and charges, then opposites attract. And since the 2 plus is farther from the minus because it's a bigger ion, then you get a less or a weaker lattice energy. Okay, and then they also said make this talk about it in terms of Coulomb's law. Coulomb's law, the force is kind of proportional to this. So these two things were the charges. So the bigger the charge difference, then the stronger the force. So if you had say magnesium and oxygen versus sodium and chlorine, okay, the 2's up here would basically result in bigger charges on top. So that would be stronger than sodium chloride. Sodium chloride only has charges of plus and minus 1, so that would be a weaker force. And then what did R stand for? If you've got 2 ions, right? Then how do I show R in those pictures? What is R?
I do not remember.
Does this make sense?
Oh, distance?
It's the distance. It's called the bond radius.
Oh yeah.
Okay, and actually, so because Coulomb's law could also work for not necessarily for atoms, but this actually is how a lot of things, capacitors work or magnets work. But if you have a bunch of pluses or a positive region and a negative region separated, there's some attraction there, and the attraction also depends on this distance r. And they call it r. It stands for radius. In some cases, they should use the term d, but they use radius because usually when we talk about atoms and points, it's a little sphere, and then you've got this force of attraction that emanates from the middle, so it's kind of radial. But r stands for distance. So you should just be comfortable looking at an equation. What happens as the distance gets bigger? What happens to force?
Does it get bigger?
Well, look, so think math. What happens if the bottom of this fraction gets big? What happens?
Smaller.
Yeah, the F gets smaller. Or what happens if Q gets big?
Then it gets big?
Then F gets big because it's in the numerator. So that's called the direct relationship. So you could say force is directly proportional to both charges, and it's inversely proportional to the distance. So, and that's called Coulomb's. There you go. And I don't think Coulomb's law, don't believe they give you the formula on the formula sheet. I could be wrong, but it's kind of a fundamental law. So they probably expect you to just know that as the distance between things gets bigger, the force gets small, and as the charge gets bigger, the force gets big. And that explains a lot of they're called periodic trends. Okay, so just since we've got time and I don't have any other questions like copied. Actually, I'm lying. I do have Savannah's question that we could talk about that you sent me. But
oh yeah.
Yeah, but since we have a little time, let's just talk about some periodic trends. So atom size. As you go across a period,
They get smaller, right?
They get smaller. Why do atoms get smaller? So say as you go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's period 2. As you go from left to right, why do they get smaller?
You're at.
Go ahead. Go ahead, Arthur.
It's because you're adding more and more protons that causes it to pull in the electron.
Correct. More protons with no additional, and we had a word for this, shielding. Do you guys remember what shielding is?
Yeah, it's the inner ones shield
Correct.
the outer ones from getting pulled.
Correct. So since our core electrons, the ones in the middle, as you go across this period, since we're not changing the core electrons, the shielding doesn't change, but you do add in a bunch more protons. And so, yeah, so you get this more attraction. So they pull all those electrons in tighter. Okay, what happens to electronegativity?
It decreases?
Think about what are the most electronegative elements?
The ones that are farther down?
Electronegative are the ones that really want electrons. So electronegativity as you go across, so think about this one, like lithium, which has 1 valence electron, versus fluorine, which has 7. Which one of those desires electrons more?
Fluorine.
Fluorine, because it's really close to achieving a full octet, right?
Yeah.
So then this one is highly electronegative because it really wants its electron, and lithium is basically not electronegative at all because it doesn't want electrons. It wants to get rid of its electron. So this has a low electronegativity.
Okay, that makes sense.
Okay, so let's look at these two, and then let's go the other direction. What happens if you go down a group? So like in terms of like lithium, sodium, potassium, rubidium, cesium. What happens to atom size?
It gets bigger?
Yep, and that's because more electron shells, right?
Yeah.
So these are big and these are small. And then what happens to electronegativity as you go from, say, we won't look at lithium because it's not very electronegative, but let's look at fluorine, chlorine, bromine, iodine. Those are all group 7. So they all have 7 valence electrons. Which one wants electrons the most out of that group?
Iodine?
Fluorine is the one. Why would fluorine want it more than iodine?
Is it because it has less shells?
Correct.
Okay.
So this one has less shielding.
Oh.
Yeah, and actually, how about this? How about it? Yeah, it just experiences less shielding. That's probably the best response. They all experience similar amounts of shielding because they all have like full cores and they all have 7 valence electrons. But the electrons on the outside, like iodine is such a big element that these 7, 3, 4, 5, 6, 7, that those electrons are so loosely held, and the protons that are in the middle are so buried that it can't attract the last electron as easily. It still wants one, okay? It's still electronegative, but it's not as electronegative as fluorine.
Okay, that makes sense.
Yep. Okay, and then this also goes with ionization energy. Ionization energy, and that looks like this. Oops. That looks like, say you have a default atom. Let's just call it atom A. Okay. So to ionize it, I've basically ripped an electron off of it. First of all, is that an endothermic or exothermic process?
Is it endothermic?
Yep. Because I would need to add energy, right, to shake the electron free. So this is a endothermic process, and then let's just talk as you go across a period. Okay, does it get easier or harder to ionize it? To remove an electron, does it get harder or easier to remove an electron as you go to the right?
It gets harder.
Yep, hard to ionize because you can't remove electrons from things like fluorine very easily. Okay, these are easy to ionize. So now, in terms of ionization energy, which one is going to require more energy?
The ones that are hard to
The ones
ionize?
that are hard to ionize. So then this would have a high or a large ionization energy, and these would have a low ionization energy. Okay, and then going down, where are the hardest ones to ionize? Near the top of the periodic table or near the bottom? Which ones are the
Near
hardest?
The bottom?
The bottom ones are low. Why are the bottom ones easy to ionize? Why would the bottom ones be easy to remove?
Is it because it has more shielding?
Yeah, and what's true about the distance from the outer shell, which is the valence shell? What's true about the distance to the valence shell from the nucleus when you're down at the bottom of the periodic table?
It's super large.
It's super large. So these are far away. Electrons are far away from the nucleus. So they're easy to remove, resulting in a low ionization energy. And then these ones, okay, and then these ones are high ionization energy because they are close to the nucleus.
So is that why you guys were talking about the corners?
Why we're talking about what?
The corners, of the periodic table?
Yes. Yeah, like the corners of the periodic table are the extremes, right?
Yeah.
So like in terms of ionization energy, if you want like say the lowest ionization energies, you'd be looking, let's see if I can draw this right. Something like that. You'd be looking down here. This would be really low ionization energy. Okay. If you wanted really low electronegativities, it would also be down here. Low electronegativity. And if you wanted like small atomic radiuses, where are the smallest elements?
At the top?
Yeah, the top right. So these are small atoms. Okay? So those are periodic trends. And as you move, I don't know, towards those extremes, right? So if you want big atoms, you just go to the opposite corner. So big atoms would be down here, and then things with high ionization energies would be up here, and high electronegativities would also be up there.
Okay.
So that's kind of general rule of thumb, but they're going to ask more questions like, can you justify? Oh, why does fluorine have such a high ionization energy? It's because the electrons are close to the nucleus, so they're hard to remove. So they're going to want justification. So if you need, if you want, and again, this is pretty quick synopsis, you could review, they're called periodic trends. There probably will be some type of tie-in with periodic trends because it's a pretty critical part. Why do things behave the way they do? And so you can look up your chapter and read through that summary. Okay, let's see. Savannah, I can hang on a second and go through that question, but Tyler, you should try, send me a screenshot from your AP Classroom. So there was the Google Classroom assignment. Go check the Google Classroom assignment, and then for next week, Savannah and the AP College Board, they just released a bunch of practice problems for the actual test that's coming up, and so I'll be assigning some of those to look at. They have like true to form, like free response questions that will be similar to what's on the test. So that'll be our like weekly assignment for juniors, for you and Vincent, for next week.
So I was looking at the thing that they posted for the assignment,
and
it gives you a whole bunch of questions like A, B, C, D, E, and F, but it only gives you 2 images you're able to upload.
Huh. Okay. And then when you upload them, I wonder if does it send them to me as your teacher, or does it send them to like the college board, and they're gonna grade them for you.
Yeah, I don't know. I'm just gonna try one out.
Yeah, because I'm curious, because what's crazy is usually for every other question that like you guys have done, I've had to go in and say like assign. Like I've had to click a button that says unlock. But
Yeah.
for all these new ones, it said that they were gonna just make them visible to all students, regardless of what their teacher says, just so that they could prep. But they didn't tell us how we're supposed to score them or see your work or anything. So it might just be on your side. And if that's the case, and if they're gonna grade it, that's great. But if I'd really like to give feedback, because I think these are gonna be the most like they're going to be the most representative of what's on the actual test. Like what you're getting in those questions, that's what the test is going to feel like.
And after I upload it, if you don't get it, I could always screenshot the problems.
Yeah, so why don't you try and upload one, and we'll see if it shows up on my account. And if it doesn't, you can take a picture. Okay. So Tyler, go read Google Classroom, check out the assignment, and then stay posted for next week too. Okay. So, let's see. Tyler, I think if you want to stick around, then Savannah had a couple questions, and I pulled up a picture. If not, then I will see you on Monday. We'll just stick with the same schedule: 10:30 Monday, Wednesday, Friday. Let's see, Savannah. Okay, so. Okay, and this question came from the little video lecture that guy's doing, right?
Yeah.
Okay, so not the warm-up one, right? Or was it part of the warm-up one?
It was part of the warm-up, yeah.
Okay, so I can see what's going on. They took... hold on a second. Did you have equal moles of these three things?
Yeah.
Okay, and then what happened? Did you add them together, or?
So we had the chemical equation that had the equal moles and molarity and volume.
Okay.
And then they tried to find the temperature change so they could figure out Q equals MCAT.
Okay,
and then they used the Q to find the delta H of the reaction.
Yeah.
But from the Q, they changed it either positive or negative.
Okay, I know what's going on. So when we do a little chemical reaction, let's say here's the reaction: A plus B, aqueous, and let's just say it makes AB, and it's still aqueous. So you do this: you dump in, let's say, 50 milliliters of 0.1 molar A, and then you dump in 50 milliliters of, I'm gonna make it similar to theirs, 0.1 molar B. So you do equal amounts of A and B, right?
Yeah.
And let's say, so this all mixes together, and you get a graph that looks like it starts at 20 degrees and it ends up at, let's say, 45 degrees. This is Celsius, right?
Mm-hmm.
Okay, so this results in a change in temperature of 25. Okay, and we're going to assume that since these are low concentrations, that basically, I know there's chemical in there, but it's mostly water, right? Everything's dissolved in water. So this is basically like heating up 100 milliliters of water, right?
Yeah.
So here's the basis of calorimetry. We can track things about water, okay? Like it's easy for us to stick a thermometer into this cup, but it's hard for us to measure what's happening with individual chemicals and molecules. So the nice thing about that is this is always true for an energy balance, assuming you have a perfect calorimeter.
Okay.
So
why is it negative?
Well, can you understand like what's, if you think of the chemicals as like this little black box, okay? So imagine, I know the chemicals don't look like this, but imagine all the chemicals are in this black box. What is heating up the water? Why is all this blue water getting hotter?
Because the chemicals are releasing energy.
Correct. So do you see, from the chemical standpoint, they're releasing energy. From the water standpoint, what's the water doing?
It's gaining
It's
energy?
gaining energy. It's absorbing energy. Now, what's true about the amount of energy that the water gains compared to the amount that the chemicals release?
They're equal?
Because the law of conservation of energy says you can't create or destroy energy. So does this make more sense?
Yeah, that makes sense.
So what's the negative actually mean?
That it's gaining energy?
Yeah, that it's opposite direction. So if the water is losing energy, then this reaction has to gain energy. Or if this water is heating up, then that means the reaction is exothermic.
Okay.
So that's why they flipped the sign. So we can go through this now that we know, let's say Q for the water. We do this all for the water. Okay, the water was, and they actually don't call it water. Usually they call it, because it's a mixture, but they call it solution.
Yeah.
Okay, well the Q of the solution is equal to the mass of the solution times the heat capacity of the solution times the change in temperature of the solution. We know the mass. If we assume that it's like the density of water, we had 100 milliliters. 100 milliliters of water weighs roughly 100 grams. Okay, we know that since it's temperature, or sorry, since it's water, its heat capacity is 4.18 joules per gram degrees C. And we know that the temperature change was 25 degrees C. So I end up getting, I'm going to round this just because I can see, it's about 400 times, or it's about 100 times 100. So it comes out to roughly, I'm not going to calculate, it's roughly 10,000. Okay. And the grams and the degrees C cancel, so it's roughly 10,000 joules. Okay?
Yeah.
Which is 10 kilojoules. Okay, now that's how much energy the water absorbed, right?
Correct.
So once you know how much the water absorbed, then what are you going to say is true about the reaction?
So that's what the water absorbed.
Then what did the reaction do?
It's not gaining, it's losing.
Correct.
So it's exothermic?
Correct. So that's why we make it the opposite sign. Because the solution gained 10 kilojoules, that means the reaction had to lose 10 kilojoules.
So negative is...
Yep, negative is exothermic, right?
Yeah.
So this reaction is exothermic. But if you were studying the water, what just happened to, or sorry, the solution, what just happened to the solution?
It's endothermic.
Correct, because it gained. But since we're chemists, we always study the reaction.
Oh, okay.
But we can't directly, like there's no thermometer that you can stick into chemicals. So what we have to do is we make all of our measurements on the solution, and then we switch the sign because we're studying the reaction.
Oh,
that's all. Okay, and then hey, what's nice is we maybe didn't react a full mole. We didn't react a full mole of our reactants, right?
Yeah.
So what you have to do, this was for 50 milliliters of 0.1 molar A, right? So I need to know how many moles of A did I react, right? So I take 0.050 liters times 0.1 molar, which comes out to 0.005 moles. So I reacted 0.005 moles of A, right?
Yeah.
So for every 1 mole of A, I need to figure out how much energy this would release. So this was per 0.005. So when you calculate delta H, this is the formula we always use. You take your Q of reaction and you take your moles, divide by the moles reacted, and you choose a chemical that limits and account for its stoichiometric coefficient.
So if both the A and B had the same amount of moles, how do we know which one limits?
Well, and it was also 1-to-1 reaction, right?
Yeah.
So 1-to-1. So it basically, this is a perfect stoichiometry. They'd both run out, right? So
Okay.
it doesn't matter which one you use because they're both 0.005, right?
Yeah.
So, and they both have a stoichiometric coefficient of 1, which is nice. So what we do, we just go in and we take negative 10 kilojoules and we divide by 0.005 moles. And you get, that's like 20 something thousand. Let me do it so I don't mess up. Negative 10 divided by 0.005 is negative 2,000 kilojoules per mole.
Is it per mole of the reaction?
Yeah, now, so that's per mole as written. So if you react exactly 1 mole of A with 1 mole of B and form 1 mole of AB, if you do that exactly with 1 mole and 1 mole, it will release negative 2,000 kilojoules. Does that make sense?
Yeah, that makes sense.
Okay, if we would have had something like this, let me change up the 2C plus D makes CD.
So, if we were trying to figure out 3 moles of this reaction, would you just multiply by 3?
Yeah, if it said how much energy would be released if you reacted 3 moles of A with excess B, you would say negative 6,000.
Okay.
Yeah. Now, if it was something like this, let's say you did the same stoichiometry, like your same calorimetry, except this time you use, let's go through, let's say the Q of reaction was negative 10 kilojoules again. Okay, and let's say this time we reacted 0.1 molar, let's say 50 milliliters, and this time 1 molar, 100 milliliters. Okay, so we could first convert these to moles. So 0.1 times 0.050 is 0.005 moles. So I have 0.005 moles of C, right? And here I have 1 molar times 0.1 liters. So I get 0.100 moles of D. So I have basically it's like I have 20 times more D than I have C, right?
Yeah.
So what was the limiting reactant here?
But you also have 2 C's.
Well, so it takes twice as much C's, right? So if I wanted to react all of this chemical, I would need 0.2 moles of C, right?
So C is the limiting?
C is the limiting because because I don't have like anywhere near the amount, right?
Yeah.
So with that in case, to calculate delta H, I would take negative 10 kilojoules divided by, and I need to divide by 0.005 moles of C, and I also need to divide by the stoichiometric coefficient. Okay?
Oh, yeah. Okay.
So I would end up getting, so basically you account for the stoichiometric coefficient there.
Okay.
Yeah. Because for every 2 moles of C, I'm reacting and getting 10 kilojoules, or I'm getting like a certain amount. So this one comes out to, let's just double check. Negative 10 divided by 0.005 divided by 2 comes out to negative 1,000. Right? So what that's saying, and that's mole of reaction. So if I react 2 moles of C with 1 mole of D, then I release 1,000 kilojoules, right?
Yeah.
If I react, say, 1 mole of C with, let's just say, excess D, then how much would I release?
500?
Yep, 500.
Okay.
Okay. If I did, let's go to 0.5 with excess. Oops, and that's 500. So now I'm half of that, right? Then that would be 250. Yeah. Is this making sense? And then, I think I went the wrong way. Let's see, 0.005. I think I did go the wrong way.
Wait, what if you have 2 moles of C and like 3 moles of D? Is this still 1,000?
Hold on, because I got to double check, because this wasn't coming out right. I think I put the stoichiometric coefficient in the wrong spot. I had it down here, and that's not correct. I need it up here. And let me just make sure this works. So when I do this, -10 times 2 divided by 0.005 comes out to -4,000. So let's go through this exercise again. I want to make sure. So if I react perfectly 2 with 1, that would release 4,000.
Yeah.
If I do half of that, then that would be 2,000. If I do half of that, it would be 1,000, right?
Mm-hmm.
And now, hey, if I go from 0.5 down to 0.005, which moved the decimal place 2 more times, right? Then that would be 10. That would be 10. And hey, if you remember, when we based this all, when we reacted the original reaction, which was 0.005 moles, it released 10 kilojoules, right?
Oh, yeah.
So what we're saying is, yeah, if you do the full reaction amount, which was a 2-to-1 ratio, right? 2 to 1. If you do the full amount, it will release 4,000 kilojoules, and that's called kilojoules per mole of reaction. Okay, and so sorry, this was my mistake, and again, this is how I would solve it, because I don't memorize. I'm not good at memorizing. I have to work through the problem a little bit, but I don't memorize if that goes on the bottom or the top. But now looking at it, I probably, when you're calculating delta H of reaction, maybe if you commit to memory, just say Q reaction times the stoic coefficient divided by the moles of the limiting. Yep. And this is the stoichiometric coefficient of the limiting. Okay. So yeah, I would commit that to memory, or that would be a good thing to have written down as notes when you're taking the test, so that you don't, like, that would, for me, I would save myself 3 minutes worth of double checking, because I just didn't. I made the mistake. So yeah, if you have that for reference, whenever you calculate, hey, if you see something involving Q and delta H, then I would just go find that formula.
Okay, awesome.
Yeah. Okay, so I will see you guys Monday, and then Savannah, yeah, you don't have to rush through it. You're kind of the guinea pig, but when you have a chance, try submitting one of your free response questions.
Okay.
Okay. See you guys. Oh, and hey, I have on my to-do list. So when I'm out and about, because we're trying to register people for the track meet, I am gonna hide the tape measure. I don't know where, but I will send you a picture or something.
Okay.
And then I don't know if other people are registered. If you have any friends like who are running track and they want to do something, tell them to sign up, because we're gonna try this one that will probably end next week. And if it works, maybe we'll do one more and invite like all the NWalk athletes. Like we could send it out to all the coaches and have people post. So anyways, I'll be checking that this weekend, but I'll let you know when I get the tape measure out.
Okay, thank you.
Yep. Okay. Have a good weekend.
You too.
All right. Bye.